Yeah. All right. Okay. So good evening, good morning, everyone. So depends on where you are. So welcome to the CAFAT Global Conference. So this is the overall agenda. So today we will have the second preliminary talk sessions. So today we will talk about these critical inputs for CAFAT. So in the slides later, I will talk about the agenda for today and also the agenda for the next time. So today, essentially, this is the agenda. So it will be, the agenda is slightly different from what Alex will present in her talk. So after the first three individual videos, we will have 15 minutes break. You can take a break or you can go to the gather town again for the social activity. And 2 minutes before it ends, I will send an email, remind you coming back. And of course, we will also do announcement in the gather town to remind you come back. So after that, we will have 4 videos to play. So that would be the all the talks. And after that, we will get into the Q&A sessions. So please use the this Q&A box there, right? Click that, add your questions there, and then we can promote you as the co-host, and then you can ask questions. And after that, we will have the gather town social again, similar to what we have last time. And next week, this is what we will do. So very similar to the typical schedule. So we will have Greg to give his live talk. So this is not a pre-recorded video. So he will give his live talk. And after that, we will have Jim from Apple to talk about the alloy design in Apple. So one difference of this talk is his talk will only be played once. We will not record this video because this is the agreement with Apple. So the video will only be played once, but the Q&A sessions, of course, will be recorded. So later on, you can have access. So that is pretty much of the arrangement for these 2 days. And today we will have Scott and Richard to be the chair. So Scott and Richard, you can go ahead.
Excellent. Okay, so I have the honor of introducing our first speaker, the amazing Alexandra Navrotsky. So Alexandra Navrotsky was educated at the Bronx High School of Science and the University of Chicago, where she completed her bachelor's, master's, and PhD in physical chemistry. After postdoctoral work in Germany and at Penn State University, she joined the faculty in chemistry at Arizona State University, where she worked with a leading-edge team of material scientists and geochemists until her move to the Department of Geologic and Geophysical Sciences at Princeton University in 1985. She chaired that department from 1988 to 1991 and has been active in the Princeton Materials Institute. In 1997, she became an interdisciplinary professor of ceramic, earth, and environmental materials chemistry at the University of California at Davis, and was appointed the Edward Rosler Chair in Mathematical and Physical Sciences in 2001. More recently, she rejoined the Arizona State University faculty, that was in 2019, as professor in the School of Molecular Sciences and the School of Engineering, Matter, Transport, and Energy. And she is currently the director of the Center for Materials of the Universe, a cross-disciplinary center that brings together planetary science and material science. And so Alex will be giving the introduction to this round robin of presentations, and then she'll be giving her more detailed presentation after our break. So I'll begin Alex's introduction right now.
Ladies and gentlemen, it is a pleasure to talk to CalFAD. It would be more of a pleasure if I were there in person. When Axel van der Walle and I were basically invited each to give plenary talks, we decided to combine our talks to illustrate an ongoing project that we have had for many years. And this is a project then that involves us as faculty, Sergei Ushakov as a research professor now at Arizona State, and Chi-Chun Hong, who is coming to Arizona State as an assistant professor. So the project is on experimental and computational thermodynamics of refractory materials at high temperature, and we will be doing a round-robin presentation of what we are going to present. I moved to Arizona State a little over a year ago, and part of my coming here was to establish a new center for materials of the universe. This basically studies the properties of materials in the context of Earth, planetary, and exoplanetary science, and is a very exciting new field, but a little bit tangential to what we're discussing here, although the properties of materials at very high temperature are indeed crucial to understanding the evolution of planetary systems. So, next. The goals of our ongoing joint project have been to produce new and improved thermodynamic and theoretical techniques for analyzing materials at high temperature. High temperature means that entropy as well as enthalpy are important. To provide experimental determination of transformation and melting points, enthalpies and entropies of phase transitions and fusion, and thermal expansion, volumes of transition, other sorts of things that are not readily obtainable at present. Theoretical determination of these parameters, particularly things like heat capacities, which are hard to measure at temperatures above 1500 degrees C, are an excellent way of expanding the data. Comparison of theory and experiment then leads to the development and improvement of both. If we agree between theoretical and experimental calculations, we are basically happy. If we disagree, that means there's some interesting science hidden in either the techniques or the materials themselves. Our initial focus has been on rare earth oxides, but now we're expanding the project to contain nitrides, carbides, carbonitrides, zirconium and hafnium materials, and other refractories. So the round-robin presentation will be my introduction, which I'm finishing. Axel van der Walle will present a talk on high-throughput ab initio CalFAD, followed by Chi-Chun Hong, who will talk about automated in-situ calculation of high-temperature materials properties. We will then have a break for a discussion. We will then come back to the experimental thermodynamics. I will talk about calorimetric advances. We will show a short video from the NSF website that we prepared a little over a year ago on some of our high temperature techniques. Sergei Ushakov will then talk about CalFAD inputs from high temperature diffraction and thermal analysis databases. Axel will then conclude, and we will have time after this for discussion. So we are all trying to stay on a fairly strict schedule. Thank you.
All right, excellent. And so now is the next item of our agenda is we will have a presentation from Professor Axel van der Walle. Axel is a professor in the School of Engineering at Brown University and a recipient of an NSF Career Award. He completed his PhD in materials Science and Engineering at MIT in 2000 under the supervision of Gerhard Sater. And after a postdoc with Mark Asta at Northwestern, he became an assistant professor at Caltech. He then joined Brown University for early tenure, where he has been since. So just bear with me for a moment as I queue up the video.
Welcome, everyone. I'm Axel van der Waal, and today I'm going to be talking about two somewhat related topics. One of them is the high-throughput ab initio CalFAD method that I'd like to describe, and another topic is a data organization effort that we've been doing for a few years. It's called the Thermodynamic database. So I'd like to, of course, acknowledge my collaborators in my group that I've been in my group for many years and have been helping with this. And also some useful input by a lot of other collaborators from different groups around the world. And of course, our funding support, which I list below here. All right, so let's start with the first topic. So what is the motivation for doing this kind of effort here? So as you know, high throughput ab initio efforts have been making a huge impact, and you know the name A-Flow Materials Project, Open Quantum Materials Database. All of these have had, really major impact. The only thing is that typically they're limited to stoichiometric phases at 0K. There are some efforts to move away from that, but still this is kind of the center of mass of all of these efforts. So, but honestly, non-zero temperatures deserve more than zero attention. And also, as you know, most engineering materials really exploit off stoichiometries. We really love to tune material properties by adding impurities and sometimes adding them in great amount to make high entropy alloys, for instance. So essentially, the theme of this is that CalFAD really comes to the rescue in terms of that effort, where we can actually combine all of these ab initio high throughput effort with something that looks a lot like the CalFAD method. All right. So here's the general kind of framework that we use. It's not entirely new. I have to acknowledge that there's been a lot of effort in that direction before, as I mentioned here below. So essentially, the method we call here is the SQS plus SRO plus CalFAD method. So SQS is a special quasi-random structure. SRO is the short-range order, and CalFAD, well, we know what that is. Consistent writing the free energy of a phase in the following way. We have n-member free energies, which we just take from the experimental SGT data, just because that allows us to have everything in the same units and to that, we add formation enthalpies that we get from essentially ab initio calculation based on random arrangements of atoms on a lattice, but of course they're special quasi-random structures, so it's a little bit more efficient than just placing them at random. And we have a lot of experience in doing these kind of things. I'm going to talk about it a little bit more. And of course, as in any CalFAD model, we add an ideal solution formation entropy. This being not perfect, we have to add some correction for short-range order. This is actually a correction that's based on CVM. And we have a way to do this that doesn't involve many more calculation than what SQS already requires, so that's very nice. So these three first terms here that has been used by a lot of people before. That's not that new. Adding this, the short-range order correction, is somewhat new. And also we're going to push, and I'm going to explain that further. We're going to push this part a little bit more in terms of detail. So what we're pushing further here is that these SQSs that we generate, in general, they will be multi-component ordered phases, so they can have any number, not just binary. And also they have multiple sublattices. And the reason this is important is, as you know, in the compound energy formalism, CEF, we like to be able to control the composition of the different sublattices to really completely parameterize your model. And so we can actually generate SQSs where you control each sublattice separately. And that way you can get all beyond what a lot of people have been doing, which is just compute n members of an ordered phase using ab initio calculation. This actually maps out the full composition range. And of course, to that we add these short-range order correction. Typically, when you do SQS, you don't have short-range order because you assume your material is perfectly disordered. But it turns out that you can use the formation energy of an SQS to get some information about interaction. So if the formation energy of an SQS is strongly negative, that means that unlike atoms interact very strongly. So you know something about the interaction between the atoms, and from that you can actually use that to create a CVM-based correction. And the beauty of this is actually you don't even need anything more than the SQS energy to do this. So it comes really for free. I don't really have time to go into the mathematical formalism, but this is in our paper that describes all of this approach here. So one thing I want to really emphasize today is something maybe more that CalFat people will relate to. How do we handle things like non-solid end members? As you know, it's not easy to include, for instance, molecular oxygen in a ab initio calculation. That introduces a lot of issues. So we have a way to kind of handle this kind of problem very systematically. And also there's the issue of mechanical instability or mechanical stability of the end members. As you know, very often in a CalFat model, you end up having to specify free energies of things that don't exist, like FCC tungsten, for instance. So this has been a long-standing problem where CalFat extrapolations to these virtual phases disagree with naive ab initio calculation of the same quantity. And we believe we have found a fairly general and convincing answer to this. And I'm going to spend a lot of time on that particular problem. So let's first talk about the first issue, which is how do we do these SQSs? So as I said, what we have to do is sample. If you have for instance, a rock cell structure with two different sublattices here, one commented by composition X, one directed by composition Y. What we have to do is literally generate some SQSs that span both the site fraction X and the site fraction Y, and that way we can actually fit a complete CEF model from that. Obviously, we have the ability also to do this in ternary. Here, I just have a single sublattice ternary, but we can have multiple sublattice ternaries or quaternaries, anything. And we have the ability to generate these SQSs at arbitrary composition. We have attempted to create a standardization scheme where a certain level of accuracy always means a certain type of grid in composition space. So that's a kind of a nice way to not having to work every time. We have standardized these SQSs, and we've created a database of SQSs. So this is a sample of what we have. We actually have about 40 of these structures already, but each entry in this is actually many different SQS because you sample different composition space. So this is a very nice resource. It's a kind of a general database of a lot of known SQSs that we have generated, including some that are done by others. And so these are fairly advanced SQSs. They have really sometimes very complex structures, many sublattices. We have some chi phases which have many sublattices, each with their disorder. We also have things that are designed for high entropy alloys, like 5-component FCC solid solution SQSs and so forth. All right, so this is just to give you an idea of what is available already. All right, let's see this method in action. Here we're kind of revisiting some prediction made by the Curtarolo group, where they did a huge high throughput exploration of many systems, and they found some new ordered phase that were not expected or not known. And we kind of went through those and saw what happened here. So in the iridium-ruthenium system, what we found is that indeed, there are a lot of little ordered phase here, but it turns out that once you take into account entropy and use our method to formally include all of these phases in a CalFad fashion, what we find is that the disordering temperatures of all of these phases is basically extremely low. So there's very little chance that you would be able to synthesize those phases in reality. So this is a case where we are able to exclude some predictions to, as being not all that relevant for most thermodynamic modeling purposes. Now, of course, it's not always the case. There are some examples where we do find, like in the nickel-rhenium system, if we apply our method, we find that 2 of the predicted ordered phase by the Curtarolo group are actually fairly stable. Their entropy participates a little bit to that because, as you can see, there's some width to these phases here. And what is very nice, actually, is that we actually find why they were missed in the past. If we look at all the available experimental data, they just turns out to exactly just miss the transition temperatures for these other phases. So it's actually a very kind of an unexpected, beautiful result here where our prediction exactly confirms what was known, and at the same time confirms that the new prediction are probably valid and consistent with all that was known. All right, so now let's talk about issues like non-solid end members. I'm taking the example of oxygen because it's so common. And of course, we're talking about oxides in our general collaboration with Professor Nawrotsky's group. So this is very relevant to that. And we have a paper actually that is in process here that suggests a very systematic way to figure out how to get ab initio results that are easy to get and at the same time that are consistent with experiment in a very natural way. So what we do is we define a virtual oxygen in the following way. We pick two oxides, or it could be an oxide and metal, but it's, in general, it can be arbitrary two phases that have a different oxygen content. And what we say is, well, let's define the chemical potential that will stabilize in a two-phase equilibrium between these two. And we extrapolate to get the chemical potential. And we define this as our reference. Now, this reference can be both computed and it can also be measured. If you know these oxides, you could, in principle, measure everything about it, free energies and so forth. And so, of course, through calorimetry and etc. And so what we do is we actually compute formation free energies relative to this virtual oxygen here, okay? And that involves only solid state calculations, which is very nice because DFT works well for solid state calculations. And then to go to an oxygen phase in the gas, we then use the experimental difference between gaseous oxygen and this virtual oxygen, which can also be computed exactly in the same way from experimental data. So that way, we actually get back to a reference energy that is completely compatible with experimental measurements. And from the viewpoint of calculation, we only need to do solid state calculations, which is really, really nice to do. And we've tested this in many different systems. Here are two examples of Ellingham diagram that were computed and compared with the experimental results, and it's a very nice agreement. So it is really a very, very useful and powerful method. All right, let's go to a slightly more difficult problem, which is how do you handle mechanical instabilities? So the way we do this, you have to look at, see, this is a bit of an abstract space here. So the horizontal coordinates represent kind of the geometry of the phase. So you could imagine if you have just a system where you have BCC, FCC, and stability, okay, where the FCC wants to relax to BCC. So these would be related to the C over A ratio. And of course, there are multiple ways to deform. So that's why this is a whole plane here, not just a one-dimensional space. And then in the vertical axis, I have the potential energy of that system in that particular deformation state. So if you wanted to know, hey, what's the free energy or the energy of the FCC phase? Well, what you would do, you would just relax in that little pocket here. This is a pocket where the curvature is positive, so it's stable. So here everybody agrees, you just relax the system and you get your energy of the relaxed system, and that is the energy, everybody agrees with that. Now, what do you do in the unstable phase where you had the, for instance, FCC tungsten is the canonical example? Well, if you just freeze it, you get this fairly unphysical thing that does not agree at all with what the CalFAD community has been doing. If you just let it relax by breaking the symmetry, you go back to FCC. So this is not the right solution either. But what we found is that what you could do is you actually define the free energy of FCC as the minimum of all the points that are in this blue region that is defined as every place where the system does not have all of its curvature being positive. So it's the complement of these basins here, red basins here. And if you do that, you end up finding a minimum that's an inflection point. Okay, and this is a very well-defined, easy to find point in space. Okay, and that is what we will use as a definition of the energy or free energy of FCC, of an FCC phase that would be mechanically unstable. So this is just a definition so far. Why is it reasonable? Well, there are a couple of reasons why it's reasonable. One thing makes it very convenient is that if you want to now turn on the temperature and go to higher temperatures, you can easily do a harmonic expansion about this point at the boundary. And the reason it works is that you're just at the boundary between a stable and an unstable region. So in fact, the number of modes that are unstable, if you look at the phonon dispersion curve, you're just at the verge of being unstable. So there's only a few points that touch the zero axis here. So the number of modes that are unstable is actually negligible. It's a finite number of points in an infinite number of k points. And therefore, it's actually negligible, the contribution to the free energy, which means that you can just neglect them, which is very convenient. So you can do an harmonic expansion for a point that's just at the boundary of that unstable region, and that works. If you were to do that for a point inside the region of instability, then you actually cross this zero here, and you can no longer neglect these modes because an infinite number of them. Okay, so we avoid this by looking at the boundary. Now, another thing that points to this boundary being very nice, this inflection point being a very nice point to focus on, is if you look, this is now a much simpler example. I just did a cross section in one dimension, and all of these red curves here are essentially a potential energy as a function of some positioning variable, or it describes the geometry of the system. And then you have the potential energy of the vertical axis. And as you approach, say, a specific composition or a specific pressure or temperature, this potential energy surface changes up to a point where it becomes unstable. So at this point now, the local minimum here has disappeared. Now, what I point out here is if you follow the local minimum for the points that are stable, but when the stable point disappears, you start following the inflection point, it actually turns out that these are actually on a line that's continuous. And you can prove that mathematically very easily. If I look at the force on the system, which is the derivative of the potential, when you're at a point like here below, this point here is an equilibrium point, a local minimum, this is a local maximum, and this is the inflection point. And as you approach a region of instability, what happens to this graph is the following. It just goes down like this, and the stable minimum, the unstable maximum, and the inflection point just merge at a single point, which is here. And this is why these two curves join very smoothly. It turns out if you plot the energy as a function of that external variable alpha here that described the instability, you actually get a curve that actually is continuously differentiable at a point. So it's a very, very smooth extrapolation of the two. So this is a very nice property. Now, the smooth extrapolation is what is going to give us a result that I believe the CalFAT community will like. And we have actually checked that in an empirical way. So here what I've plotted is as a function of composition. So this is a ternary system where actually all elements have a different preferred lattice, right? The rhenium is HCP, tungsten is BCC, and iridium is FCC. Okay, so this is a particularly difficult case. So in green, I plot what traditionally the ab initio community would have done, which is just at, when you have an alloy, you just do a random, solid solution supercell. And then when you approach a region that's mechanically unstable, you just freeze the coordinates that are unstable to the ideal value, and you get something like this. The problem is that if you go to, for instance, the canonical case of FCC tungsten, you get this really crazy jump here where you really get a completely strange energy for FCC tungsten that does not at all agree with what you would extrapolate from what happens at other composition. Okay, and the orange plot here is what SGT predicts for this value here. Okay, now if you just do the opposite, which is allow the system to relax, so you break the symmetry and you just allow it to completely relax, then you get a slightly smoother curve, but then you actually get the wrong stable state, because for instance here you would get BCC tungsten even though you were interested in FCC. So that's the wrong thing to do as well. If you use our scheme, which is this what we call inflection detection, because it detects the inflection point, then it solves the problem, because you actually get very smooth curves at all composition. It's very, very smooth. And not only that, amazingly, it agrees very well with SGT. You see the yellow and the blue completely agree here and here. Same here, it's a bit of a worse disagreement, although there are other assessments that actually gives it a much better agreement here. Sometimes these assessments agree all, and then, so overall, it's a very good agreement here. Now, of course, this is only 3 elements. So what happens when you actually go through all those elements that have either FCC, BCC, or HCC as a stable phase? And here's what it looks like. So this is an example where, so from HCP to FCC, there's no instability. So this is kind of an idea of what you get when there is no instability. This is the kind of quality of agreement you would expect. If you now do our scheme, this is what you get. So the top of these dotted line are actually the unrelaxed structure. So what the ab initio community would have traditionally done. Okay, and when you use our inflection detection scheme, you get to that cross here, and you can see that the agreement is significantly better for all HCP to BCC kind of instability. And we do that for all of these other things. So again, this is a case with no mechanical instability. This is the FCC to BCC case, and we get a lot significantly systematic better agreement with the SGT values when we do our scheme, rather than just the naive unrelaxed ab initio value. And same thing now for BCC to HCB instabilities and BCC to FCC instabilities. Again, we get for almost all elements an improved agreement with experiments. All right, so this is kind of, so when you do this, you can actually, when you put all of these techniques together, you can actually do high throughput CalFAT from ab initio computations. And here are two examples of such systems that have been computed. And so here's the copper, platinum, and tungsten system. Here's the iridium, rhenium, and tungsten system. And again, these are very difficult computations. We have a lot of very, complex phase, sigma, chi phase. We have all the different lattices. We have even a liquid phase that we model through MD. And this is basically what I think is the future of ab initio CalFAT methods here. We've even done a quaternary system. This is something that was done as part of an effort to find a high entropy alloy that would be a good substitute for rhenium. And here we even have, some experimental confirmation of our phase boundaries that are in very good agreement as well. So this is, of course, a Gibbs tetrahedron. All the faint lines are tie lines, and all the colored surfaces are the phase boundaries. Okay, so this is again what the kind of thing that we can fairly easily do. All right, so I have a few more minutes to talk about our other effort, which is the thermodynamic database. So this is a very comprehensive effort to kind of integrate all the data source that contains some TDB files. Okay, so there's a CalFAT journal, the supplementary information. There's a NIMS database. NIST also has a lot of such data. And we've interfaced that with the Crossref bibliographic services, and we have all of this information put together into this TDBDB, Thermodynamic Database, and that is also integrated with visualization tool. It's based also on Open CalFAT, and the thermodynamic engine that makes all of this possible is in great part Open CalFAT. We have some post-processing that allows us to get some very nice graphic out of this. So I think the best way to do now is to just show you an example of what it looks like when you access our website. So essentially, this is what the user interface looks like. You just type your elements that you're interested in. You click search, and then you get a list of all the known assessments in the database, and you can pick the one you want. For each of them, you can pick, you have a DOI access to the paper, which you can immediately download if you have, authorization to do it from your institution. You can access the TDB file directly, download it as well. You can also get the bibliographic information, and that allows you to easily cite all the sources. So really, I just have to point out this is not data scraping. This is actually data indexing. So when I point you to the data or the papers, I actually don't copy the data. I actually point to the original website. So you need to have an account to those websites to access the data, which is fine. For most of them, it's free, or it's already included with what your institution would have. So that makes it, it alleviates any kind of copyright issue. It's really just a search engine, but it's a fairly nice search engine. So not only can you do this, get to the original data, but you can also preview a phase diagram for it. And after a few seconds, it actually creates the phase diagrams like this. Okay, so this is a very quick way to generate. So in the case of ternaries, you can generate on the fly any cross section that you want. Okay, so which is very nice. It gives you much more than what you would have in a traditional handbook, right? You can't just generate cross sections on the fly as in a traditional phase diagram handbook. And of course, these are some, you can even go to higher dimensions. You can plot ternary as a function of temperatures. You can also plot quaternaries. So it's a very nice visualization tool in addition to being a nice database. All right, so, and again, just to repeat what I mentioned before, it's really a search engine. We don't gather the data, we just point to it, make it easy to find. We can generate all sorts of cross-section on the fly. You can get your TDB files directly. You can process, you can download them, process them the way you want. Makes it very easy to cite all the appropriate data source. And there's also an application programming interface to all of this. So if you are into programming instead, you can use that resource as well. All right, so as a conclusion, what we've done here, we have talked about a new finite temperature high throughput tool that's based on the SQS formalism with CVM correction to do short range order. And of course, it's also based on the CalFAT formalism, which makes all of this possible. We've also spent some time describing a theoretically justified and quite convenient definition of the free energy of mechanically unstable phase that is not only convenient, theoretically justified, but also agrees with what CalFat people have been doing for multiple decades. And that is really a first, to have all of these three features in one thing. And also I've briefly described a new CalFat tool, which is the Thermodynamic database, which is a very nice resource of all the data that our community has been generated, and it's nicely integrated in a graphical interaction interface. So thank you very much.
All right, excellent. Thank you so much, Axel, for that excellent presentation. And so we do have one more presentation before the break for the social activity on GatherTown. And just as a reminder for people, to please feel free to capture your questions, save your questions. We will have a Q&A session at the very end after all the speakers have presented. And so now we will move right into our next presentation, which will be from Dr. Chijun Hong. Dr. Hong is an incoming assistant professor of material science and engineering in the School for Engineering of Matter, Transport, and Energy at Arizona State University. Hong completed his PhD in chemistry at Caltech in 2014 under the supervision of Axel van der Walle. After a postdoc at Brown, he became a machine learning scientist at Amazon.com Incorporated. Hong's research we are going to hear a bit more about. It focuses on atomistic modeling for prediction of materials properties. He is the developer of the solid and liquid and ultra-small coexistence with hovering interfaces, or SLUSHY code, great acronym, a software package that enables first principles calculations of melting temperature, heat of fusion, heat capacity, thermal expansion, and other material properties. And so please, once again, bear with me for just a moment as I queue up the video.
Hello, I'm Chijun Hong. I'm Axel's postdoc at Brown University, currently a machine learning scientist at Amazon, and I'm thrilled to be joining ASU this fall as an assistant professor in material science and engineering. Today, I'll be talking about using automated first principles calculations, especially density functional theory and molecular dynamics, to compute high temperature materials properties both accurately and cost effectively that can serve as inputs for CalFat. As Axel just pointed out, non-zero temperatures deserve more than zero attention. For properties such as thermal expansion and heat capacity, the harmonic approximation starts to disappoint us at high temperature. When melting is involved, we need free energy of the liquid phase, and the computation becomes a lot more challenging. Indeed, we call melting temperature a high-level quantity that requires extensive sampling of the configurational space. Over the past few years, we built an accurate and efficient method that handles these challenging tasks. I'll first introduce our method, small cell coexistence, and our automated tool, SLUSHY. I'll then give a few examples of the applications to show its capabilities. Let's first take a look at traditional methods. There are two major traditional methods for melting point calculations. One is the free energy method. That is, we locate the intersection of the free energy curves of the solid liquid. Three drawbacks for this method. First, the two curves usually cross at a very small angle, so a small bias in free energy may result in a large error in melting temperature. Second, it is expensive to calculate the free energy of liquid. Third, error cancellation is unlikely, since the free energies of the solid liquid are calculated separately using different methods. The other traditional method is large size coexistence, which is generally considered the gold standard. In this method, we search for stabilized solid-liquid coexistence, so the corresponding temperature is the melting point. But the large system size, which is at least 1,000 atoms, and the long MD trajectory, which is up to 100 picosecond in this case, they just make it too expensive for DFT calculations. Our new method runs solid-liquid coexistence in a small cell. The small system size is a big advantage because it is much faster and it makes DFT calculations feasible. But this small system size also poses problems. For example, the solid-liquid interfaces are too close, so they are not stable. We cannot maintain solid-liquid coexistence in a small cell. Rather than coexistence, the system now prefers a single phase, either a pure solid or a pure liquid. So we cannot simply copy the traditional method. But we find that the motion of the interface and the distribution of the final states will reflect the free energy difference between the solid and liquid. So if we run many MD duplicates, we can fit the melting temperature based on the statistical distribution of the final states. Here we have 16 MD duplicates, starting from half solid, half liquid. At this trial temperature, we'll see 5 of them ending in pure liquid, with higher enthalpies and disordered structures, while the rest 11 ending in pure solid. And we can fit a melting temperature based on the statistical distribution of the final states. This movie shows the time evolution of these MD duplicates. We have 1, 2, 3, 4, 5 liquids, and the rest are solids. And note here the small system size and the short time scale, which indicates the low cost of these simulations. Compared to traditional large-size coexistence, instead of running one long MD trajectory on a large supercell, we now run multiple short MD trajectories on small systems, and we save lots of computational cost in this way. Here's an example using an EAM in potential. Each green mark corresponds to one MD trajectory. For temperature near the melting point, we see a distribution of the final states, and we can fit a melting point as the blue curve. For DFT calculations, the process is similar, with the only difference being that we cannot afford to sample so many data points, so the statistical error will be larger. The method calculates more than melting temperature. Each green mark gives us an estimate of enthalpy, either the solid or the liquid. We fit the red lines separately. The slope is heat capacity. The vertical distance between the two lines is heat of fusion. I'll get a similar plot by replacing enthalpy with volume. Then I'll also have thermal expansion. We put what we have into an automated code, and we call it Slashy. Slashy is available for download. It is fully automated with interface to VASP. So just let it run for a few days, and it will give us back a good melting point. Precision depends on how many MDs are sampled. There's always a trade-off between cost and accuracy, such as the finite size error. The general guideline is that we achieve 100 Kelvin accuracy with about 100 atoms. We are excited to see lots of visitors and downloads over the past few years, and happy to see it helps others in the community make progress in their own research. Next, I'd like to give you a few examples. The first one is about prediction of the world's highest melting temperature. The Hafnian tantalum carbon system was considered the material with the world's highest melting point at around 4,000 Kelvin. We studied contributing factors for the high melting point and proposed that Hafnian carbon-nitrogen system has even higher melting temperatures. Our method enables us to run dozens of melting point calculations at various compositions, and we fit a quadratic function to locate composition that corresponds to the highest melting point. Our computations were later confirmed independently by two experiment groups. Let's first take a look at experiment number 1 on hafnium carbide and tantalum carbide. Because the two figures are mirror image, I flip one of them so we have hafnium carbide on the left and tantalum carbide on the right for both figures. Starting from tantalum carbide, melting temperature first increases, then drops. But as it approaches hafnium carbide, melting temperature increases again. There was a discrepancy between my computation and previous experiment data regarding hafnium carbide. The latest experiment suggests my computation is correct. In experiment number 2, the authors compared the melting temperatures of hafnium carbide and hafnium carbon nitride. They confirmed that hafnium carbon nitride has higher melting temperature. Note the chemical composition of their samples and how close it is to my prediction. The second example I'd like to present is a quaternary alloy. We show that the alloy has a relatively high melting point, and along with other favorable properties we found in experiment, this alloy could be a promising material to replace rhenium in rocket engine. Next example is about high pressure melting curve. We explore melting of simple metals under extremely high pressure conditions and discover unusual properties of melting curves. Previously, the general consensus was that melting curves increases indefinitely along with pressure for most metals, except for alkaline metals, which have this unique feature of re-entry melting that reaches a maximum and then decreases. Our calculations suggest that both magnesium and aluminum share the same feature on melting curve as sodium, but at extremely high pressure conditions. And this is probably the reason these properties are not yet discovered in experiment. Based on the trend, we propose that this special shape of melting curve might be a universal feature for all metals. My last example is about thermodynamic properties of refractory oxides at high temperatures. Slushy is also capable of calculating other materials' properties, such as thermal expansion, heat capacity, heat diffusion, etc. This fits very well into our collaboration with Alex and Sergey's group at UC Davis and now at ASU. In this collaboration, we rely on a mutual corroboration, that is, computation from ours and experiment from theirs to determine the thermodynamic properties of oxides, such as rare earth oxides, hafnium oxide, zirconia, ytteria, etc. I should point out that these materials have extremely high melting points above 2000 Kelvin and challenging experiment conditions. So a mutual corroboration from both computation and experiment really helps us make sure our findings are correct. Alex and Sergey will be discussing more details of this work later in the second half of the session. I'll end my talk with a project that the four of us are currently working on. On the left is phase diagram I get from Sergey that contains all stable phases and temperatures for I203 for all the lanthanide series elements. On the right is volume based on automated DFT-MD simulations. The process is so automated that we calculate simultaneously volume and energies on hundreds of possible combinations of materials and temperature conditions. We look forward to further application of the method to serve the CalFAT community with accurate data inputs.
The schedule take a 15-minute break. I do want to apologize. We may have done our schedule arithmetic a little too quickly. And so the time shown on the schedule that we showed you was not quite correct. However, we are following the same schedule of events. And so what we are going to do now is we are going to take a 15-minute break. And so by my math, we will reconvene. We might go to 17 minutes. Just to clarify, that will put us at, let's see, that's 6:10 p.m. Pacific time, 9:10 p.m. Eastern time. And so we will reconvene this session in 15 minutes and pick up with the remainder of the program. So I do encourage you to join the Gather Town if you are not already, to engage in the designated social activity for the conference and to maybe chat with some of your fellow attendees. And as always, of course, if you have any questions, please feel free to reach out to any of the organizers, either on Zoom or on GatherTown, and we will do our best to help you. So thank you, and see you in 15 minutes.